One last thing I should clarify from matrix notation is that when we're talking about the size of a matrix, as it were, we refer to that as its order. And when we talk about order, we refer to it in terms of the number of rows and columns it has. So when we say a matrix has order m times n, that means it has m rows and n columns. And in particular, if m and n are the same, we say that the matrix is square, and sometimes we'll just identify the order of it in terms of the one value, because there's no need to put it in terms of both when they're the same. But anyway, the next thing we're going to talk about here is what's hopefully kind of a natural quality to think of, that is equality of matrices, because now we have some sense of what a matrix is in its own terms, so it would seem reasonable to wonder how we can get two matrices that are fundamentally the same, in the same way that words or variables can be, or numbers for that matter. And that's kind of what we're thinking of here. So it would make sense that two matrices are equal if they have the same things in the same places, and that's essentially what this property is. More exactingly, we say that two matrices A and B are equal if they have the same order, so all the pieces would fit in the same way, and for element Aij in matrix A, that is some element in position ij in the matrix, Aij is equal to Bij in matrix B. That is, for the pieces in A at the same spots as pieces in B, you get the same thing. So, same pieces in the same places. The notation's a little bit dense for this definition, but if you just think about it logically, it should feel fairly reasonable. And from here, we can think of a pretty brief and basic example with these two matrices here, where we want to determine what x has to be in order for them to be equal. And in this case, we've got the first step that we really need, that is, they're the right size. Each has 2 rows and 3 columns, so we would say that they are both 2 by 3 matrices. And then from there, we essentially just have to make sure that all the pieces fit in the right way. And for the most part, they do. We've got a 2 and a 2, a 1 and a 1, a 5 and a 5, 3, 3, negative 2, negative 2. The only concern is that bottom right corner, the slot in the second row, third column, element 2, 3, as it were. For the one on the left, that's 4. For the one on the right, that's x. And really, you don't need to overthink it here, because you need the same things to be in the same places. If you want these matrices to be equal, x just has to be equal to 4. And that would make this picture work. However, this can go a bit wrong fairly easily. For example, if we were to take that one on the left and just seemingly spin it a little bit to make a 3-row, 2-column matrix, a 3 by 2 matrix, even though it has all the same elements and the positions feel similar, we can't say that the one we have over here is equal to the one we have over there, or the other one that we were originally questioning, because we can't have the exact same places to make those comparisons, even though all of the numbers are the same. They're not in the same place. So the two matrices are not equal. And that's something we're going to keep seeing here, something we're going to be hammering home a lot more as we get to these operations, these more arithmetic things that we can do in here, that it's not just the values that matter, it's where the values are that tell us a great deal about what we're trying to do.